Thanks to modern telescopes and scientific ingenuity, we've discovered thousands of exoplanets, planets outside our solar system, some of which lie remarkably close to us, within just a few dozen light-years. These nearby worlds are more than just dots on a scientist's chart. They are dynamic, alien places with their own weather, climates, and quirks. Some might have oceans hidden beneath icy crusts, others could be scorched by their sun's intense flares, and a few may even offer conditions where life could thrive. Let's journey through the strange and fascinating planets that orbit the stars closest to our solar system, exploring their mysteries and what they reveal about the possibilities of life beyond Earth. A new frontier, exploring the closest exoplanets to Earth. In cosmic terms, 10 parsecs, about 32.6 light-years, is a remarkably short distance. The light from stars within that range takes only a few decades to reach us, a blink of an eye compared to the billions of years the universe has existed. To put it in perspective, the Voyager 1 spacecraft, humanity's most distant emissary, would take over 75,000 years to travel just 1 light-year. And yet, these close exoplanets are within the reach of our telescopes and technology. They provide a window into planetary systems that are still within our detailed observational grasp, a chance to study worlds in greater depth than ever before. Exoplanets within this range offer a glimpse into the diversity of planetary systems. In our own solar system, we have a wide variety of planets, from the rocky worlds of the inner solar system to the gas giants farther out. But how typical is our system? The nearby exoplanets help us answer that question. These worlds come in all shapes and sizes, from scorching hot giants orbiting close to their stars to icy planets farther out. Some may even resemble Earth, with rocky surfaces and temperatures that could allow liquid water to exist. By studying these planets, we learn not just about them, but about the possibilities for planets throughout the galaxy. The search for life beyond Earth is one of the most profound scientific quests of our time, and these close exoplanets are among the best places to look. Many of them orbit stars that are smaller and cooler than the Sun, known as M-type or red dwarf stars. These stars are abundant in our galaxy and often host planets in their so-called habitable zones, the regions around a star where conditions might be just right for liquid water to exist. Water, as we know it, is essential for life, and these habitable zones are the starting points for exploring whether these planets could support living organisms. They are also ideal laboratories for understanding how planets form and evolve. For example, scientists can study their atmospheres to learn about their chemical compositions and weather patterns. Observing the light from these planets' host stars as it filters through their atmospheres reveals the presence of gases like oxygen, carbon dioxide, and methane. These gases not only tell us about the planet's environments, but could also provide clues about biological activity. Their proximity means that they are bright enough for detailed study with current and next-generation telescopes. The James Webb Space Telescope, or JWST for instance, is already providing insights into the atmospheres of exoplanets, and upcoming missions like the European Extremely Large Telescope will push these studies even further. These powerful instruments allow scientists to probe the surfaces and atmospheres of these planets with unprecedented precision. In the future, missions designed to directly image exoplanets could even reveal surface features, such as oceans, continents, or clouds. The proximity of these exoplanets also makes them realistic targets for interstellar probes. While the technology to send spacecraft to another star is still in its infancy, ideas like Breakthrough Starshot envision tiny light-driven probes traveling at a significant fraction of the speed of light. These probes could potentially reach the nearest stars within a human lifetime, providing direct data about their planets. While this vision is still decades away, the exoplanets within 10 parsecs are the natural first destinations for such missions. Some of these nearby worlds orbit so close to their stars that their surfaces are molten, their atmospheres blasted away by intense radiation. Others are far enough out to be frozen solid, locked in eternal winter. There are planets with masses several times that of Jupiter, and others smaller than Mercury. some orbit in resonances, with their movements intricately linked to those of their neighbors. These variations push the boundaries of our theories about how planets form and what conditions they can endure. By comparing the atmospheres of nearby exoplanets to those of Venus, Earth, and Mars, scientists can refine their models of planetary atmospheres and climates. This, in turn, helps us better understand the factors that make a planet habitable or uninhabitable. The question of whether we are alone in the universe has profound philosophical and scientific implications. Nearby exoplanets offer the best chance of answering that question in the foreseeable future. Even if we don't find life, studying these planets helps us understand the conditions under which life could arise and thrive. And if we do find evidence of life, even in its simplest forms, it would forever change our understanding of the universe and our place within it. Why 10 parsecs? The significance of our stellar neighborhood. The decision to focus on planets within 10 parsecs is not arbitrary. It is a deliberate choice shaped by the capabilities of our current technology and the scientific goals of exoplanet research. At this distance, planets are close enough for detailed observation while still providing a diverse sample of planetary systems. Observing exoplanets is a challenging task. These worlds are small and faint compared to the stars they orbit. The light from a star can outshine its planets by millions or even billions of times, making them incredibly difficult to detect. For planets within 10 parsecs, however, their relative closeness makes them appear brighter and easier to study. Their proximity allows astronomers to use advanced techniques, such as measuring tiny wobbles in a star's motion, or observing slight dips in brightness when a planet passes in front of its star. These methods, known as radial velocity and transit photometry, are most effective for nearby stars, where the signals are stronger and clearer. The stellar neighborhood within 10 parsecs is home to a wide variety of stars. This diversity is crucial for understanding how different types of stars influence the formation and evolution of planets. For example, red dwarf stars, which make up the majority of stars in this range, are cooler and smaller than the Sun. Their planets tend to orbit closer, often within the habitable zone, where liquid water might exist. Studying these systems helps scientists explore how planets adapt to the intense magnetic activity and stellar flares that are common in red dwarfs. By contrast, the few Sun-like stars within this distance offer a chance to compare other solar systems to our own, helping us understand how unique or typical our planetary arrangement might be. Another advantage is the opportunity to study multiple systems in detail. The relatively short distances mean that light from these stars and their planets reaches Earth with less distortion from interstellar dust. This clarity allows astronomers to analyze the chemical composition of planetary atmospheres more precisely. Using instruments like the JWST, scientists can look for specific molecules, such as water vapor, carbon dioxide, and methane. These molecules not only reveal the conditions on these planets, but can also hint at processes like volcanic activity, weather patterns, or even biological activity. The proximity of these planets also enables more accurate measurements of their physical characteristics. For example, the mass of a planet can be determined by observing how much it tugs on its star, and its size can be calculated from the amount of starlight it blocks during a transit. Combining these measurements gives scientists an idea of the planet's density, which in turn reveals whether it is rocky like Earth, gaseous like Jupiter, or something in between. These details are harder to obtain for planets farther away, where the signals are weaker and more difficult to interpret. There are approximately 300 stars within this distance, and many of them have been found to host planets. This range includes a mix of solitary stars, binary systems, and even a few triple star systems. Each of these setups offers unique insights into how planets form and survive in different gravitational environments. By focusing on this neighborhood, scientists can study a wide range of planetary systems without being overwhelmed by the vast number of stars in the galaxy. Among these nearby worlds, there are gas giants larger than Jupiter, small rocky planets similar to Earth, and intermediate types known as super-Earths and mini-Neptunes. Some of these planets orbit their stars in tight, scorching hot paths, while others lie farther out, in cold, icy regions. This variety helps scientists refine their models of planet formation, showing how different factors, such as the mass of the star, the presence of other planets, or the composition of the protoplanetary disk, shape the final outcome. Proxima Centauri b, the closest known exoplanet, orbits within the habitable zone of its red dwarf star. While the planet's proximity to its star means it is likely tidally locked, with one side always facing the star, scientists are exploring whether its atmosphere could redistribute heat and support conditions for liquid water. Similarly, planets like LHS 1140b and TRAPPIST-1e offer exciting opportunities to study potentially habitable worlds around stars very different from our Sun. Another reason for the focus on nearby planets is the potential for direct imaging. Observing an exoplanet directly, separately from the light of its star, is one of the most challenging tasks in astronomy. However, for planets within 10 parsecs, the angular separation between the planet and its star is slightly larger, making it easier to block out the starlight and capture an image of the planet itself. Direct imaging not only allows scientists to study the planet's atmosphere and surface features, but also provides a more complete picture of its environment, including its temperature and potential weather patterns. The accessibility of planets within 10 parsecs also makes them prime candidates for future exploration missions. Concepts like breakthrough starshot envision sending small, fast spacecraft to the nearest stars, carrying instruments capable of collecting data and sending it back to Earth. While such missions are still in the early stages of development, the proximity of these planets makes them realistic targets for interstellar exploration within the next century. Proxima Centauri, the nearest star with a planetary surprise. Sitting just over 4 light-years away, Proxima Centauri, the closest star to our Sun, is part of the Alpha Centauri star system, a trio of stars that includes Alpha Centauri A and Alpha Centauri B. While Proxima Centauri is not visible to the naked eye, it holds a special place in the search for planets beyond our solar system. In 2016, astronomers discovered Proxima b, a planet orbiting this dim red dwarf star, sparking excitement about its potential to support life. Proxima Centauri is a small and cool star compared to the Sun. Classified as a red dwarf, it has a much lower temperature and brightness, which means its habitable zone, the region where conditions might allow liquid water to exist, is much closer to the star. Proxima b orbits within this habitable zone, completing a full orbit in just 11.2 Earth days. At this distance, the planet receives enough energy from its star to keep its surface temperatures in a range where water, if present, could remain in liquid form. This proximity to the star also makes Proxima b one of the easiest exoplanets to study with our current technology. The discovery of Proxima b was made using the radial velocity method. Astronomers observed tiny wobbles in Proxima Centauri's motion caused by the gravitational pull of the orbiting planet. These measurements revealed that Proxima b has a minimum mass about 1.2 times that of Earth, suggesting it is likely a rocky planet. Proxima Centauri, like many red dwarfs, is highly active, frequently releasing powerful bursts of energy known as stellar flares. These flares emit intense radiation, including ultraviolet and X-rays, which can be harmful to planetary atmospheres and surface conditions. If Proxima b has an atmosphere, it would need to be robust enough to withstand these constant bombardments. Without an atmosphere, the planet's surface would be exposed to harsh radiation, making it unlikely to support life as we know it. The planet's close orbit means it is likely tidally locked, with one side always facing the star and the other side in permanent darkness. This tidal locking could lead to extreme temperature differences between the day and night sides. However, if Proxima b has an atmosphere, it might help redistribute heat around the planet, creating more stable conditions that could support liquid water. Scientists are also investigating whether Proxima B's magnetic field, if it exists, could provide protection against the star's flares. A strong magnetic field, like Earth's, can deflect charged particles from stellar winds and flares, shielding the planet's atmosphere from being stripped away. Proxima Centauri's frequent flares pose a challenge for future exploration. Any missions to Proxima b, whether by telescopes or spacecraft, would need to account for the unpredictable bursts of radiation from the star. These flares can temporarily overwhelm observations and make it harder to gather clear data about the planet's atmosphere or surface conditions. However, advancements in telescope technology are helping scientists overcome these challenges. Luyten star, a quiet red dwarf with a habitable zone contender. Luyten star, a quiet red dwarf, is another fascinating neighbor in our stellar backyard. Located just over 12 light-years from Earth, it stands out among red dwarfs for its low activity. Unlike many of its counterparts, which often release bursts of radiation in the form of flares, Luyten star is remarkably calm. This tranquility has made it an attractive target for astronomers searching for planets where conditions might allow for life. Among its planetary companions, one stands out. Luyten b, a potentially habitable world in its star's habitable zone. Luyten star is a smaller, cooler star compared to the Sun. Its low luminosity means that its habitable zone is much closer to the star. Luyten b, the planet of interest, orbits within this region, completing one orbit every 18.6 Earth days. At this distance, the planet receives a level of energy from its star comparable to what Earth receives from the Sun, putting it in the range where liquid water could exist on its surface. This placement immediately drew attention when Luyten b was discovered, as it is rare to find planets in the habitable zone of red dwarfs that also orbit relatively quiet stars. The stability of Luyten star plays a crucial role in making Luyten b a compelling candidate for further study. Many red dwarfs, despite their long lifespans, are known for frequent and powerful flares that can strip away planetary atmospheres and make conditions inhospitable. Luyten star, on the other hand, exhibits much lower levels of activity, providing a more stable environment. This calmness gives any atmosphere that Luyten b might have a better chance of surviving over time, which is an important factor when considering the planet's potential for habitability. Luyten b is slightly larger than Earth, with a mass about 2.9 times greater. This places it in the category of super-Earths, planets that are larger than Earth, but smaller than the ice giants like Neptune. Its size suggests that it could have a rocky composition, similar to Earth, but with a stronger gravitational pull due to its greater mass. This stronger gravity could help Luyten b retain a thicker atmosphere, providing additional protection from any remaining stellar activity and creating more stable surface conditions. Tidal locking is common for planets orbiting close to red dwarfs. If Luyten b is tidally locked, the side facing Luyten star would be much warmer, while the dark side would be significantly cooler. However, if the planet has an atmosphere, it could help redistribute heat between the two sides, moderating the temperature extremes and potentially creating habitable conditions in certain regions. At around 8 billion years old, Luyten star is older than the Sun and has been burning steadily for eons. This incredible lifespan provides planets like Luyten b with an extended period to develop and evolve. The star's quiet nature means that its planetary system has likely remained relatively undisturbed over time, offering a stable environment for potential habitability. The calmness of Luyten star also makes it an excellent target for future observations. Detecting specific gases such as oxygen or methane could hint at the presence of biological activity on Luyten b, though such findings would require careful interpretation. Preliminary evidence suggests that there may be additional planets orbiting Luyten star, though their characteristics are not yet well understood. The potential presence of multiple planets raises questions about the dynamics of the system and how planets interact with each other over time. If confirmed, These additional planets could provide further opportunities to study the processes that shape planetary systems around quiet red dwarfs. The relative brightness of Luyten's star compared to other red dwarfs also makes it easier to study, providing clearer signals when observing its planets. These factors combine to make Luyten's star and its planetary system a priority for scientists exploring the potential for life beyond our solar system. Tau Ceti's dusty secrets and its planet's survival challenges. Tau Ceti, one of the closest G-class Sun-like stars to Earth, lies just 12 light-years away, and its spectral similarity to our Sun make it an enticing subject for study. However, Tau Ceti also harbors something that sets it apart from our solar system: an unusually dense debris disk filled with dust, rock, and other particles. This debris not only shapes the environment of the Tau Ceti system, but also creates significant challenges for all the planets that exist there. The debris disk around Tau Ceti is far more massive than the asteroid belt or Kuiper belt in our solar system. Observations suggest it contains about 10 times the mass of our solar system's Kuiper belt, making it a hazardous region for planetary orbits. This abundance of material raises questions about how planets form and survive in such an environment. The high density of debris increases the likelihood of collisions between objects, which can disrupt the orbits of forming planets or even destroy them entirely. For planets that do manage to form and stabilize within this environment, the dense debris disk poses ongoing threats. Impacts from asteroids and comets are likely to be far more frequent than in our solar system. Such collisions can have profound effects on a planet's surface, atmosphere, and habitability. On Earth, asteroid impacts have played a role in shaping the planet's geological history and even influencing the evolution of life. The asteroid that contributed to the extinction of the dinosaurs is a stark example. In the Tau Ceti system, where debris is much more abundant, these events could occur more regularly, potentially resetting any progress toward habitability. Repeated collisions with large objects could strip away a planet's atmosphere, especially if it lacks a strong magnetic field to protect it. Without an atmosphere, the planet would be exposed to the harsh radiation from its star, making it difficult for life to gain a foothold. Even smaller impacts can release significant amounts of energy, generating heat, and possibly altering the planet's climate in ways that are hard to predict. Despite these challenges, the presence of a dense debris disk is not necessarily a deal-breaker for habitability. It may even play a role in fostering conditions for life under the right circumstances. For instance, comets and asteroids are rich in water and organic molecules, the building blocks of life. In our own solar system, it is believed that early collisions with comets delivered much of Earth's water. If similar processes occur in the Tau Ceti system, they could help seed any rocky planets with the materials needed for life to develop. The question, then, is whether the benefits of such deliveries outweigh the destructive potential of frequent impacts. The debris disk also complicates efforts to directly observe planets around Tau Ceti. The abundance of dust scatters light from the star, creating a bright and noisy background that makes it difficult to distinguish planets from the surrounding material. Advanced techniques, such as high-contrast imaging and spectroscopy, are required to tease out the faint signals of planets amid this chaos. Despite these difficulties, astronomers have identified several candidate planets in the Tau Ceti system, including some that may lie within the star's habitable zone. In the case of Tau Ceti, the habitable zone is slightly closer to the star than Earth is to the Sun, due to Tau Ceti's slightly lower luminosity. However, the presence of the dense debris disk complicates the habitability equation. Planets within this zone would need to contend with frequent impacts and the possibility of disrupted orbits caused by gravitational interactions with the debris. Another factor to consider is the role of planetary migration. During the early stages of a star system's development, planets often shift positions as they interact with the surrounding disk of gas and dust. In the Tau Ceti system, the dense debris disk could have significantly influenced the migration of planets, pushing them closer to or farther from the star. This process could have profound implications for the system's architecture and the potential habitability of its planets. For instance, a planet that formed within the habitable zone might have been forced out of it, while a planet that formed farther out might have migrated into the zone, bringing with it a different set of conditions. The interaction between planets and the debris disk can lead to the formation of resonances, where planets and debris particles settle into stable orbital relationships. These resonances can help clear certain regions of the disk, reducing the likelihood of collisions in those areas. However, they can also concentrate debris in specific regions, creating zones of heightened danger. Understanding these dynamics is crucial for assessing the long-term stability and habitability of planets in the Tau Ceti system. While our solar system's debris belts are relatively sparse today, they were likely much denser in the past. The late heavy bombardment, a period of intense asteroid and comet impacts that occurred about 4 billion years ago, may have been driven by interactions within the early Kuiper belt. By studying systems like Tau Ceti, astronomers can gain insights into how such periods of bombardment influence the evolution of planets and the development of life. On one hand, Tau Ceti's dense debris disk creates a hostile environment that makes the survival and habitability of planets more difficult. On the other hand, it provides a natural laboratory for studying the processes that shape planetary systems. By examining the interplay between the debris disk and the planets in the Tau Ceti system, scientists can better understand the delicate balance of forces that govern the formation and evolution of planets. Teegarden's star, a treasure trove of Earth-like worlds. Teegarden's star is one of the smallest and faintest stars in our galactic neighborhood. Located just 12.5 light-years from Earth, this dim red dwarf went unnoticed for much of modern astronomy until its discovery in 2003. Despite its unassuming nature, Teegarden's star has drawn attention for hosting not one, but 2 planets with striking similarities to Earth. These planets, Teegarden B and Teegarden C, have opened new doors in the search for habitable worlds. Teegarden's star is so faint that it cannot be seen with the naked eye, even from dark sky locations. It is a red dwarf with only about 9% of the Sun's mass, making it one of the least massive stars known. Its low luminosity means its habitable zone, the region where liquid water could exist on a planet's surface, lies very close to the star. This proximity places both Teegarden B and C within ranges that make them intriguing candidates for further study. Teegarden B, the innermost of the 2 planets, orbits its star in just 4.9 Earth days. Despite this short orbital period, the planet receives an amount of stellar energy comparable to what Earth receives from the Sun, thanks to the dimness of its host star. This puts Teegarden B firmly within the habitable zone, where temperatures could allow for liquid water to exist on its surface. Its mass, estimated to be similar to Earth's, suggests it could have a rocky composition, further increasing its potential for habitability. Teegarden C, the second planet, orbits slightly farther out with a period of 11.4 Earth days. It receives less energy from the star than Teegarden B, placing it near the outer edge of the habitable zone. This cooler position might make it more comparable to Mars in terms of surface temperatures, but it still falls within the range where liquid water could potentially exist under the right conditions. Like its sibling, Teegarden C is thought to be rocky, with a mass close to that of Earth. What makes the Teegarden system particularly fascinating is the proximity of the 2 planets to each other. Their orbits are close enough that their gravitational interactions could play a role in shaping their dynamics. While these effects are likely subtle, they could influence the stability of the planet's orbits over time. Teegarden's star itself is remarkably stable. Unlike more active stars like Proxima Centauri, it shows little evidence of frequent flares or high levels of radiation. This calmness increases the likelihood that Teegarden B and C could retain atmospheres. The relatively short distances between Teegarden's star and Earth mean that signals from its planets, whether atmospheric or geological, are easier to detect compared to those from more distant systems. These observations could provide valuable data on the composition, climate, and potential habitability of Teegarden B and C, offering a deeper understanding of the conditions that allow planets to support life. Instruments capable of analyzing the light passing through these atmospheres during transits could detect signs that might hint at biological activity. At approximately 8 billion years old, the star is older than the Sun and has been shining steadily for much of the galaxy's history. The small size and low brightness of Teegarden's star make it a challenging target for detailed observation, but its proximity to Earth offers significant advantages. The discovery of two Earth-like planets in such a small system is a reminder of the diversity and abundance of planetary systems in our galaxy. It demonstrates that even the faintest stars can host worlds with remarkable similarities to our own. Teegarden's star and its planets represent a unique opportunity to study the factors that contribute to habitability in environments vastly different from our solar system. Proxima b, a potentially habitable world under constant flare threats. Proxima b orbits Proxima Centauri at a distance of only about 0.05 astronomical units, much closer than Mercury is to the Sun. This tight orbit means that Proxima b completes a full revolution around its star in just 11 Earth days. At such a short distance, the gravitational forces between the planet and the star are immense, likely causing Proxima b to be tidally locked. This means one side of the planet always faces the star in perpetual daylight, while the other side remains in constant darkness. Its proximity to Proxima Centauri also exposes it to a harsh and unpredictable environment. Red dwarf stars are known for their flares, and Proxima Centauri is no exception. The star frequently releases powerful bursts of radiation and charged particles, far more intense than anything the Sun produces. These stellar flares can increase the star's brightness dramatically in just a matter of minutes, and emit high levels of ultraviolet and X-ray radiation. For Proxima b, these flares are a constant threat. The planet's close orbit means it is bathed in the radiation from these outbursts, which can have devastating effects on its atmosphere. High-energy particles from the star can strip away atmospheric gases over time, particularly lighter elements like hydrogen. If Proxima b started with an atmosphere similar to Earth's, it might now be much thinner or even non-existent due to this relentless bombardment. Without an atmosphere, the surface of the planet would be exposed to intense radiation, making it extremely difficult for life to survive. Despite these challenges, some scientists believe Proxima b could still host conditions suitable for life, especially if it has certain protective factors. A strong magnetic field, for instance, could help shield the planet from the worst effects of the stellar flares. Earth's magnetic field plays a similar role, deflecting charged particles from the Sun and preventing them from stripping away our atmosphere. If Proxima b has a similar magnetic field, it might retain enough of its atmosphere to support life. Another possibility is that life on Proxima b, if it exists, has adapted to the extreme environment. On Earth, there are organisms known as extremophiles that thrive in conditions once thought to be uninhabitable. Some live in acidic hot springs, others in the freezing vacuum of Antarctica, and some even deep beneath the ocean floor, where they are exposed to intense pressure and no sunlight. Life on Proxima b might have developed similar adaptations, radiation and temperature extremes. The planet's tidal locking means that the side facing Proxima Centauri would be much hotter, potentially scorched by the star's energy, while the far side would be frozen in darkness. However, there might be a region between these extremes, known as the terminator line, where conditions are more moderate. This thin band of twilight could offer a stable environment where liquid water might exist and where life could potentially thrive. Proxima b's surface conditions are still largely unknown, but scientists are exploring the possibilities through advanced computer models and observations. Water vapor in the atmosphere could play a critical role, helping to regulate the planet's climate and create pockets of habitable conditions. If the planet has a rocky surface with large oceans, these could help moderate the temperature variations caused by its tidal locking. Oceans can absorb and store heat, releasing it slowly over time and potentially creating a more stable environment. However, if Proxima b is dry, it might be less likely to support life. On Earth, some microorganisms have evolved mechanisms to repair DNA damage caused by radiation. Others use pigments or protective structures to shield themselves from harmful ultraviolet rays. Life on Proxima b might have developed similar strategies, or it could exist underground or underwater, where it would be shielded from the worst of the radiation. Its location in the habitable zone and its proximity to Earth make it an ideal candidate for detailed study. Scientists are already planning missions that could provide more information about this intriguing world. One possibility is to send tiny spacecraft equipped with cameras and sensors to Proxima b, propelled by powerful lasers to achieve high speeds. These spacecraft could reach the planet within a few decades, providing humanity with its first close-up look at an alien world. Luyten b, the curious case of an exoplanet with Earth-like potential. Luyten b has a mass very close to that of Earth, suggesting that it could have a rocky surface rather than being a gaseous planet like Neptune. This similarity immediately raises the possibility of conditions that might support life. The planet's size and density could allow it to maintain an atmosphere, an essential feature for regulating surface temperatures and potentially supporting complex chemistry. While its exact composition remains unknown, scientists speculate that its surface might include rocky landscapes, possibly with water in liquid form if the atmospheric pressure and temperature are suitable. The location of Luyten b in its star's habitable zone adds to its allure. For Luyten's star, which is much cooler and dimmer than the Sun, this zone is closer to the star than Earth is to the Sun. Luyten b completes one orbit in just about 18 days, a stark contrast to Earth's 365-day year. Despite this short orbital period, the planet receives a level of stellar energy comparable to what Earth receives from the Sun. The combination of its location in the habitable zone and its Earth-like mass suggests that conditions might be right for water to exist on its surface. Water is considered a key ingredient for life, as it facilitates the complex chemical reactions necessary for biological processes. If Luyten b has an atmosphere that can trap heat effectively, it might support temperatures warm enough for water to remain in liquid form. Unlike more active red dwarfs, Luyten's star is relatively quiet, with lower levels of stellar flares and radiation. The stability of Luyten's star enhances the chances that Luyten b could maintain an atmosphere and support liquid water over long periods. However, Luyten b's close proximity to its star likely means it is tidally locked, with one side perpetually facing the star while the other remains in constant darkness. This phenomenon creates extreme contrasts in temperature and light between the two hemispheres. The planet's habitability could depend on the presence of strong wind patterns that help redistribute heat from the day side to the night side. If the planet has an atmosphere, it could experience unique weather patterns driven by the stark temperature differences between its hemispheres. Strong winds might sweep across the terminator line, creating zones of relative stability where temperatures are more moderate. These transitional regions could be key areas to study, as they might offer the most favorable conditions for life to exist. The type of gases present in Luyten b's atmosphere could significantly influence its surface conditions. For example, a thick atmosphere rich in greenhouse gases like carbon dioxide could trap heat effectively, keeping the planet warm enough for liquid water even on the night side. On the other hand, a thinner atmosphere might struggle to retain heat, resulting in more extreme temperature variations. Determining the composition of Luyten b's atmosphere will be a major goal for future observations, as it holds the key to understanding the planet's potential for habitability. Red dwarfs are known for their long lifespans, often burning for tens of billions of years. This extended time frame offers a stable environment where life could potentially arise and evolve. However, the early stages of a red dwarf's life are often marked by higher levels of stellar activity, which could strip away a planet's atmosphere or bombard its surface with harmful radiation. Understanding how Luyten b has managed to survive and maintain its current conditions, if it indeed has an atmosphere and water, could reveal much about the resilience of planets around red dwarfs. The study of Luyten b is still in its early stages, but the planet has already become a focal point for astronomers using advanced telescopes and observation techniques. These observations might also help determine whether Luyten b has any moons or other companions, which could influence its environment and dynamics. Teegarden b and C, a dual dance in the habitable zone. Two planets, Teegarden b and Teegarden C, orbit Teegarden star, and both are positioned within the habitable zone. This unique configuration of two potentially Earth-like planets so close to one another has sparked immense interest among astronomers. The interaction between these two worlds, combined with their position around a calm red dwarf, raises questions about their climates, their potential for habitability, and how their proximity to each other might influence their environments. Teegarden b is the closer of the two planets to its star, while Teegarden C orbits just slightly farther out. Both planets are thought to have masses similar to Earth's, which suggests that they are rocky and might possess solid surfaces. Their location in the habitable zone means they receive enough energy from their star to potentially support liquid water on their surfaces, assuming they have atmospheres capable of retaining heat. Teegarden b and Teegarden C are close enough that they could exert significant gravitational influence on one another. These gravitational interactions might cause slight variations in their orbits, known as orbital resonances, which could impact their climates over time. For example, if their orbits become slightly elliptical due to these interactions, the planets might experience variations in temperature as they move closer to or farther from their star. This could create seasonal-like effects, even on a planet that is otherwise tidally locked to its star. Tidal forces caused by the gravitational pull of a neighboring planet can generate heat within a planet's interior. This process, known as tidal heating, has been observed in moons within our solar system, such as Io, which experiences intense volcanic activity due to the gravitational influence of Jupiter and its other moons. If similar forces are at play in the Teegarden system, they could keep the interiors of these planets warm, potentially supporting subsurface oceans or volcanic activity. Such internal heat sources could play a crucial role in maintaining habitable conditions, even if the surface temperatures are less favorable. Unlike many red dwarfs, which are prone to intense flares and radiation bursts, Teegarden's star is also relatively quiet. This stability increases the likelihood that any atmospheres on Teegarden b and C have remained intact over time, shielding the planet's surfaces from harmful radiation and allowing for more stable climates. The quiet environment provided by the star makes it easier for scientists to study the planets without the interference of sudden stellar activity, offering a clearer view of their potential habitability. The climates of Teegarden b and C would depend heavily on their atmospheres, if they have them. An atmosphere thick enough to trap heat could allow for liquid water to exist, even on a tidally locked planet. Without an atmosphere, however, the surface of these planets could be starkly divided. If both planets have atmospheres, their proximity might lead to interesting exchanges of material between them. In our solar system, there is evidence that meteorites have traveled between Earth and Mars, carrying material from one planet to the other. A similar process could occur in the Teegarden system, with asteroids or comets transferring material, including potentially life-bearing compounds, between Teegarden b and C. This exchange could increase the chances of life developing or spreading within the system, making it an even more compelling target for study. While both planets are within the habitable zone, their slightly different distances from the star could result in varying surface conditions. Teegarden b, being closer to the star, might have warmer temperatures, while Teegarden C could be cooler. This difference could lead to a diversity of environments, increasing the chances that at least one of the planets has conditions suitable for life. If both planets are habitable, the Teegarden system could offer a rare example of two life-supporting worlds existing side by side. Studying the Teegarden system also provides valuable insights into the formation and evolution of planetary systems around red dwarfs. Red dwarfs are the most common type of star in the galaxy, and many of them are expected to host planets. By understanding the dynamics of the Teegarden system, scientists can gain a better understanding of how planets form and interact around these small stars. This knowledge could help identify other promising systems and refine the search for habitable worlds. Wolf 1061c, a planet teetering on the edge of habitability. Wolf 1061c is a planet that has captured attention due to its location near the inner edge of the habitable zone around its host star, Wolf 1061. This red dwarf star lies about 14 light-years from Earth. Wolf 1061c's size and position initially made it a promising candidate for potential habitability. However, as scientists delved deeper into its characteristics, they began to realize that its proximity to the star might create a very different environment than first imagined. Wolf 1061c is slightly larger than Earth, which places it in the category of super-Earths. Its increased mass suggests it could have a stronger gravitational pull, which might help it retain a thicker atmosphere. A substantial atmosphere is often considered a positive trait for habitability, as it can provide insulation and protection from harmful radiation. But the planet's position so close to its star complicates the picture. The inner edge of the habitable zone is a precarious location where temperatures can rise quickly, pushing a planet toward conditions more like those on Venus than Earth. If a planet is too close to its star, the increased stellar energy can cause water to evaporate and escape into space. On Earth, water vapor in the atmosphere contributes to the greenhouse effect, trapping heat and maintaining a stable climate. On Wolf 1061c, the amount of heat from its star could amplify this effect dramatically, leading to what is known as a runaway greenhouse effect. A runaway greenhouse effect occurs when a planet's atmosphere becomes so saturated with heat-trapping gases that temperatures spiral out of control. On Venus, this process turned what might once have been a temperate world into a sweltering inferno with surface temperatures hot enough to melt lead. Scientists worry that a similar fate might await Wolf 1061c, given its position close to its star. If this is the case, any water that once existed on the planet's surface may have long since boiled away, leaving behind a dry and inhospitable environment. The potential for a runaway greenhouse effect on Wolf 1061c depends on several factors, including the planet's atmosphere, its geological activity, and its interaction with the host star. If the planet has a dense atmosphere rich in carbon dioxide, it could trap heat more effectively, pushing the planet closer to Venus-like conditions. On the other hand, if Wolf 1061c has a thinner atmosphere, or one dominated by reflective gases like sulfur dioxide, it might retain a cooler climate. These details remain unknown, but they are crucial for determining the planet's true nature. Another factor to consider is the activity of Wolf 1061 itself. Red dwarf stars are known for their variability, often emitting powerful flares that can strip away a planet's atmosphere over time. However, Wolf 1061 is relatively quiet compared to some other red dwarfs, which could give Wolf 1061c a better chance of maintaining its atmosphere. The stability of the star increases the likelihood that any atmospheric composition present on the planet has persisted for billions of years, providing a stable environment for scientists to study. One hypothesis is that Wolf 1061c could exist in a state of partial habitability. While the planet's surface might be too hot for liquid water, there is a chance that more temperate conditions could exist in its upper atmosphere. On Venus, scientists have theorized that certain layers of the atmosphere might be cool enough to support microbial life. A similar situation on Wolf 1061c could mean that life, if it exists, has adapted to survive in the planet's skies rather than on its surface. If the planet has active volcanism, it might release gases that contribute to the greenhouse effect, further warming the planet. Alternatively, volcanic activity could provide nutrients that sustain microbial life, as seen in hydrothermal vents on Earth. The presence of tectonic activity might also indicate a dynamic interior, which could influence the planet's ability to sustain a magnetic field. A strong magnetic field would be crucial for protecting the planet's atmosphere from being stripped away by stellar winds. Its position near the inner edge of the habitable zone provides valuable insights into how planets respond to intense stellar radiation and heat. By studying Wolf 1061c, scientists can learn more about the processes that determine whether a planet becomes a temperate world like Earth or a hostile one like Venus. This knowledge can be applied to other exoplanets, helping to refine the search for truly habitable worlds. Even small differences in distance from a star or atmospheric composition can have profound effects on a planet's climate and habitability. The study of this super-Earth underscores the importance of understanding not just the location of a planet within the habitable zone, but also the many other factors that contribute to its environment. The proximity of Wolf 1061c to Earth makes it an accessible target for detailed observation. These observations could analyze the planet's atmosphere, searching for signs of water vapor, carbon dioxide, or other gases that might indicate habitability. They could also reveal whether the planet has clouds, which play a significant role in regulating temperature by reflecting sunlight and trapping heat. Proxima B's atmosphere. Could it survive the stellar tempest? The ability of Proxima b to maintain its atmosphere would depend on several factors. One of the most important is the presence of a magnetic field. On Earth, the magnetic field acts as a protective shield, deflecting charged particles from the solar wind and preventing them from eroding the atmosphere. If Proxima b has a strong magnetic field, it could play a similar role. However, the generation of a magnetic field depends on the planet's internal structure and geological activity. Magnetic fields are typically produced by a dynamo effect in a planet's core. For this to occur, the core must be at least partially molten and in motion, creating electrical currents that generate a magnetic field. While Proxima b is similar in size to Earth and might have a similar internal structure, there is no direct evidence yet of a magnetic field around the planet. If it lacks this protective shield, its atmosphere would be far more vulnerable to the star's flares and winds. Another factor is its gravitational pull. The planet is slightly more massive than Earth, which means it exerts a stronger gravitational force. This could make it harder for lighter gases to escape into space, even under the influence of stellar radiation. A thicker atmosphere, rich in heavier gases like carbon dioxide, might also be more resistant to being stripped away. Such an atmosphere could still support a greenhouse effect, potentially allowing liquid water to exist on the surface. If the planet's atmosphere is dominated by gases that absorb ultraviolet radiation or other forms of high-energy radiation, it could help shield the surface from the star's flares. On Earth, the ozone layer performs this role by absorbing much of the sun's harmful ultraviolet radiation. If Proxima b has developed a similar layer, it might provide some protection against Proxima Centauri's frequent outbursts. If the planet formed with a thick atmosphere, it might have been able to withstand some of the early, more intense activity of Proxima Centauri. Red dwarfs are known to be particularly active in their youth, with frequent and powerful flares. A robust initial atmosphere, combined with a strong magnetic field, might have allowed Proxima b to retain enough of its atmosphere to remain habitable over time. Proxima b could have also replenished its atmosphere through outgassing. If the planet has an active interior, it might release gases like carbon dioxide, water vapor, and methane into the atmosphere over time. This process could help replace any gases lost to space, maintaining a dynamic atmosphere that evolves alongside the star's activity. The presence of volcanic activity would also indicate a geologically active planet, which might increase the likelihood of other processes that support habitability. Proxima B's proximity to its star also raises questions about the role of radiation in shaping its environment. While high levels of radiation are generally seen as a barrier to life, some scientists speculate that they could also drive chemical reactions that produce complex organic molecules. On Earth, radiation has been shown to play a role in the formation of certain prebiotic compounds. If similar processes occur on Proxima b, they might contribute to the planet's potential for life, even in an otherwise harsh environment. Proxima b's atmosphere, if it exists, would be a testament to the resilience of planets in the face of harsh stellar environments. Its ability to withstand the stellar tempest of Proxima Centauri would provide valuable insights into the factors that contribute to planetary habitability. Whether it has managed to maintain this delicate balance remains one of the most compelling questions in the study of nearby exoplanets. Signs of clouds or oceans. Decoding Luyten b's atmosphere, located within the habitable zone of its host star. Luyten b could, in theory, support liquid water under the right conditions. The possibility of clouds or oceans on this distant world opens up fascinating questions about its climate, surface reflectivity, and overall potential for habitability. The presence of an atmosphere on Luyten b is not guaranteed, but if it exists, its composition would play a critical role in determining the planet's climate. Depending on the balance of greenhouse gases like carbon dioxide, methane, or water vapor, the planet's surface could range from warm and temperate to icy and barren. If clouds form in such an atmosphere, they could have a dual effect. Thick clouds might trap heat, creating a greenhouse effect that warms the surface. On the other hand, highly reflective clouds could increase the planet's albedo, bouncing starlight back into space and cooling the surface. If the planet has active geological processes, such as volcanism, these could release gases into the atmosphere, providing the raw materials for cloud formation. Alternatively, if Luyten b has a large ocean, evaporation could feed a continuous cycle of cloud formation and precipitation, much like Earth's water cycle. The height, density, and composition of these clouds would shape the planet's climate and weather patterns, possibly creating zones of warmth or regions of perpetual chill. An ocean on Luyten b would be a game-changer in the search for life. Oceans stabilize climates by absorbing and redistributing heat, making them a key ingredient for sustaining habitability over long periods. If Luyten b hosts a global ocean or smaller seas, these could moderate its temperature and create a more uniform climate across the planet. Ocean currents, driven by the planet's rotation and wind patterns, might further help in transporting heat from the star-facing side to the cooler regions, ensuring that no area becomes too extreme for potential life. Determining whether Luyten b has clouds or oceans requires a careful study of its albedo, the fraction of starlight it reflects. A high albedo could indicate a surface covered by ice or thick clouds, while a low albedo might suggest darker materials like rock or liquid water. Spectroscopic observations can reveal the composition of the reflected light, helping scientists identify specific molecules in the planet's atmosphere. For example, water vapor absorption features in the spectrum would hint at the presence of water in some form, whether in clouds or oceans. Another key observational technique is transit spectroscopy, which involves studying the starlight that filters through Luyten b's atmosphere as it passes in front of its star. This method can detect the fingerprints of atmospheric molecules, providing direct evidence of what gases are present. If clouds are thick enough, they might block certain wavelengths of light, creating distinctive patterns in the spectrum. These patterns would help scientists infer the altitude, density, and composition of the clouds. If Luyten b does not transit its star, direct imaging becomes the next best option. Advances in telescope technology, like the development of high-contrast imaging systems, allow scientists to isolate the faint light reflected by exoplanets from the overwhelming brightness of their host stars. By analyzing this light, researchers can estimate the planet's albedo and look for variations that might indicate the presence of clouds or oceans. Observations over time could reveal changes in brightness due to weather patterns or surface features, providing further insights into the planet's environment. Even if Luyten b lacks liquid water on its surface, other types of oceans could exist. For example, a layer of liquid methane or ammonia, similar to the lakes on Saturn's moon Titan, might cover parts of the planet. These exotic liquids would reflect sunlight differently from water, creating unique spectral signatures that could be detected with current or future instruments. Such an environment would be unlike anything on Earth, but could still support forms of life adapted to extreme conditions. By comparing Luyten b to planets with similar properties, scientists can begin to identify patterns and trends that define habitable environments. These insights help refine models of planetary climate and guide the search for life in the universe. The thin atmosphere of Ross 128b, a clue to its past. About 11 light-years away, Ross 128b orbits its host star, Ross 128, at a distance that places it within the habitable zone. Yet the planet's atmosphere, or what remains of it, raises critical questions about its past and how its environment has evolved over time. A thin atmosphere, if confirmed, could provide essential clues to the forces that have shaped this intriguing exoplanet. Atmospheres regulate surface temperatures, shield the planet from harmful radiation, and can even support the chemical reactions necessary for life. A thin atmosphere, however, poses challenges. It may struggle to retain heat, leading to wide temperature swings between day and night. It may also lack the pressure needed to keep liquid water stable on the surface. If Ross 128b's atmosphere has thinned over time, understanding why and how this occurred could reveal much about its history. One possible explanation lies in the activity of its host star. Unlike some other red dwarfs, Ross 128 is considered relatively quiet, with fewer stellar flares than its more active counterparts like Proxima Centauri. But during the first billion years of a red dwarf's life, it can be far more active than it is today. Intense stellar winds and frequent flares could have bombarded Ross 128b, stripping away lighter atmospheric molecules like hydrogen and helium. This process, known as atmospheric escape, is particularly effective on planets that lack strong magnetic fields. Without this protective shield, the planet's atmosphere would have been exposed to relentless erosion, gradually thinning over time. If Ross 128b formed with a thick atmosphere, it might have lost much of it during this turbulent period. Ross 128b is slightly larger than Earth, with an estimated mass of around 1.4 Earth masses. This increased mass suggests it has stronger gravity, which should help it hold onto an atmosphere. However, gravity alone may not be enough to counteract the effects of stellar radiation and winds, especially during the star's more active phases. The balance between these competing forces would have shaped the planet's atmospheric evolution, determining how much of its original atmosphere remains today. If Ross 128b has or had active volcanoes, they might have offset some of the atmospheric loss caused by stellar activity. Over time, however, volcanic activity tends to decline as a planet's interior cools. If Ross 128b's volcanic activity has diminished, its ability to replenish its atmosphere would also have decreased, leaving it more vulnerable to thinning. Instruments capable of analyzing the light that passes through or reflects off a planet's atmosphere can detect the presence of specific gases. These observations could confirm the state of Ross 128b's atmosphere. They might also identify signatures of processes like photodissociation, where intense radiation breaks down atmospheric molecules, further contributing to atmospheric loss. If Ross 128b's atmosphere is indeed thin, It raises questions about the planet's surface conditions. The side facing the star could become scorching hot, while the far side plunges into freezing darkness. Such conditions would create a challenging environment for any form of life, particularly complex organisms. However, microbial life, if it exists, might find refuge in subsurface habitats or within localized pockets of more stable conditions. Even if the planet's surface is inhospitable, liquid water might persist beneath the surface, protected from the harsh, stellar environment. Subsurface oceans, heated by geothermal energy, could provide a stable environment for life. Similar scenarios have been proposed for icy moons in our solar system, such as Europa and Enceladus. If Ross 128b has a thin atmosphere but retains subsurface water, it could still be a candidate for habitability. Planets evolve alongside their stars, shaped by the interplay of stellar activity, geological processes, and atmospheric dynamics. Understanding where Ross 128b falls on this timeline requires piecing together clues from its current state and comparing it to similar exoplanets. Wolf 1061c's greenhouse effect, a Venusian twin. The possibility of a runaway greenhouse effect, similar to what occurred on Venus, is a central question in understanding Wolf 1061c's environment. If such a phenomenon has taken hold, it could transform this seemingly promising exoplanet into a sweltering, inhospitable world. A runaway greenhouse effect happens when a planet's atmosphere traps so much heat that it becomes self-reinforcing. On Venus, this process began with an abundance of water vapor, which is a potent greenhouse gas. As solar radiation heated the planet, more water evaporated into the atmosphere, amplifying the warming. Eventually, temperatures became high enough to boil away any remaining surface water, leaving behind a thick atmosphere dominated by carbon dioxide and sulfuric acid clouds. Venus now experiences surface temperatures exceeding 450 degrees Celsius, making it the hottest planet in our solar system, despite not being the closest to the Sun. Wolf 1061c might face a similar fate due to its location near the inner boundary of its habitable zone. Being closer to its host star means it receives significantly more stellar radiation than Earth does from the Sun. If the planet has large amounts of water, the intense heat could lead to rapid evaporation, injecting water vapor into the atmosphere. This vapor could then trap more heat, accelerating the greenhouse effect. Over time, this feedback loop could cause the planet to lose its water entirely, leaving behind a dry, overheated surface. If the planet has a thick atmosphere rich in carbon dioxide, it might already be well on its way to becoming Venus-like. However, if other gases, such as nitrogen or even reflective aerosols, dominate the atmosphere, they could mitigate the warming. Clouds, for example, can reflect a significant amount of incoming starlight, potentially cooling the planet. The balance between these competing effects would determine the planet's overall climate. Red dwarfs emit most of their energy in the infrared spectrum, which interacts differently with planetary atmospheres than visible light from stars like the Sun. Infrared radiation is absorbed more efficiently by greenhouse gases, potentially intensifying the warming effect. However, red dwarfs are also cooler than stars like the Sun, which means that planets in their habitable zones receive less energy overall. This duality makes predicting the climate of planets like Wolf 1061c challenging. If Wolf 1061c formed with a significant amount of water, it might have retained some of it in subsurface reservoirs, even if surface water has been lost. Subsurface water could remain stable in cooler regions or under high-pressure conditions. Similarly, active volcanoes could release gases into the atmosphere, influencing the planet's climate over time. On Earth, volcanic activity has both warmed and cooled the planet at different times in its history, depending on the balance of gases released. Despite the challenges posed by its proximity to its star, there are scenarios in which Wolf 1061c might avoid a runaway greenhouse effect. If the planet has a robust magnetic field, it could protect its atmosphere from being stripped away by stellar winds. Red dwarfs are known for their stellar activity, including flares that can bombard nearby planets with high-energy particles. A strong magnetic field would deflect these particles, preserving the atmosphere and maintaining more stable conditions on the surface. Another mitigating factor could be the presence of reflective surface materials, such as ice or certain minerals, that increase the planet's albedo. A high albedo surface would reflect more of the incoming stellar radiation, reducing the overall warming effect. However, this would depend on the planet's geological and climatic history, as well as the composition of its surface materials. By comparing Wolf 1061c to Venus and other planets with similar conditions, scientists can refine their models of atmospheric evolution and habitability. These comparisons help identify the tipping points that lead to runaway greenhouse effects, offering valuable lessons for studying exoplanets and even for understanding Earth's own climate. Observations of Wolf 1061c are still in their early stages, but future missions and telescopes hold promise for unlocking its secrets. Instruments capable of analyzing the planet's atmosphere, such as spectrographs, could detect key gases and determine their relative abundances. These data would provide a clearer picture of whether Wolf 1061c is more like Venus, or if it has managed to avoid the same fate. Small changes in atmospheric composition, stellar radiation, or geological activity can have profound effects, tipping a planet toward habitability or rendering it uninhabitable. For Wolf 1061c, this balance hangs in the interplay between its position, its atmosphere, and the influence of its host star. Whether it turns out to be a Venusian twin or something entirely different, its study will deepen our understanding of the diverse and dynamic nature of planets beyond our solar system. Teegarden b, the best candidate for life beyond Earth. The first thing that makes Teegarden b special is its Earth-like characteristics. The planet is almost identical in size to Earth, with a mass that suggests it has a solid rocky surface. This is a crucial factor when considering the potential for life, as a rocky surface could support the presence of liquid water. In addition, its orbit around Teegarden's star places it squarely in the habitable zone, the region around a star where temperatures might allow water to remain in liquid form. Water is considered a fundamental ingredient for life as we know it, and Teegarden b's location makes it a prime candidate for hosting this essential element. Teegarden b's proximity to its star also offers unique advantages. It orbits very close to Teegarden's star, completing a full orbit in just a few days. While this might seem extreme compared to Earth's year-long orbit, it's quite typical for planets around red dwarf stars. Teegarden's star is much cooler and dimmer than the Sun, so a close orbit doesn't necessarily mean the planet is scorching hot. In fact, the conditions on Teegarden b are estimated to be within a range that could support life, with surface temperatures potentially similar to those on Earth. Teegarden's star, being a red dwarf, has a long lifespan and will last for tens of billions of years. This gives planets like Teegarden b plenty of time to develop and sustain life, assuming the conditions are right. Unlike more active red dwarfs, Teegarden's star appears to be relatively quiet, with fewer flares and less intense radiation. This relative calm could create a stable environment for life to emerge and thrive. Because the planet orbits so close to its star, it may be gravitationally locked. Understanding whether Teegarden b has an atmosphere and what it's made of will be a key focus for future studies. If Teegarden b does have an atmosphere, a balanced mix of gases, including oxygen and carbon dioxide, could create conditions suitable for life as we know it. Observations of the planet's atmosphere could also reveal biosignatures, chemical traces that might indicate the presence of living organisms. For example, the simultaneous presence of oxygen and methane in an atmosphere is considered a strong indicator of biological activity, as these gases tend to react with each other and would need to be replenished by ongoing processes, potentially life. The possibility of a biosphere on Teegarden B is one of the most exciting prospects in exoplanet research. A biosphere refers to the regions of a planet where life can exist, including its surface, atmosphere, and potentially subsurface environments. If Teegarden B has a biosphere, it could be home to a wide range of life forms, from simple microorganisms to more complex organisms. However, without direct evidence, these ideas remain speculative. Understanding the conditions on Teegarden B will help scientists refine their models of what a biosphere might look like on an exoplanet. Can life thrive around red dwarfs? Lessons from our closest exoplanets. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They are smaller, cooler, and less luminous than stars like our Sun. These stars often host planets, many of which orbit within the habitable zone. While this makes red dwarfs an appealing target for finding life, they also present unique challenges that could hinder habitability. One of the defining characteristics of red dwarfs is their low luminosity. These stars emit only a fraction of the light that the Sun produces, which means their habitable zones are located much closer to the star. Planets in these zones typically have orbits that take only a few days to complete, far shorter than Earth's year-long journey around the Sun. Because the planets are so close to their stars, gravitational forces can cause one side of the planet to always face the star, while the other side remains in perpetual darkness. This creates stark temperature contrasts, with one side potentially scorching hot and the other freezing cold. Winds and atmospheric circulation could create a more temperate twilight zone along the boundary between the day and night sides, where conditions might be more stable and conducive to life. Many red dwarfs are highly active, especially in their younger years, emitting powerful flares of ultraviolet and X-ray radiation. These flares can strip away a planet's atmosphere over time, leaving it exposed to the harsh conditions of space. Whether planets around red dwarfs can maintain powerful magnetic fields is an open question. Their close orbits could make them more vulnerable to magnetic interactions with the star, potentially weakening or disrupting their protective barriers. One of their most significant traits is their longevity. Unlike larger stars that burn through their fuel quickly and have relatively short lifespans, red dwarfs can shine for tens to hundreds of billions of years. This extended stability provides a much longer window of time for life to potentially develop and evolve. In contrast, stars like the Sun have lifespans of about 10 billion years, which limits the time available for complex life to emerge. Studies have shown that red dwarfs are more likely than other types of stars to have planets in their habitable zones. This abundance increases the chances of finding worlds where the conditions might be right for life. While many are known for their flares, there are quieter red dwarfs with less intense activity. This reduced stellar activity could make it easier for planets to retain their atmospheres and develop more hospitable conditions. In these quieter systems, the risks associated with radiation and atmospheric loss are significantly lower, increasing the likelihood that life could emerge. Some studies suggest that even if a planet loses its atmosphere to stellar activity, it could potentially regain it through processes like volcanic outgassing. Additionally, subsurface environments, such as underground oceans or pockets of liquid water beneath a planet's surface, could provide refuges for life. These hidden environments would be shielded from radiation and extreme temperature fluctuations, offering stable conditions where microbial life might thrive. One of the most exciting aspects of studying red dwarf systems is the possibility of discovering life forms that are adapted to extreme conditions. On Earth, extremophiles demonstrate the incredible resilience of life. From microbes that live in boiling hot springs to those that survive in the freezing cold of Antarctica, life has shown a remarkable ability to adapt. Planets around red dwarfs might host similar extremophiles, capable of withstanding high radiation levels, extreme temperature differences, or other challenging conditions. These organisms could provide insights into the diversity of life and its ability to persist in seemingly inhospitable environments. Variable stars and their impact on planetary systems. Unlike stars with steady outputs, variable stars experience significant fluctuations in brightness over time. These changes can happen on timescales ranging from minutes to years and can vary in intensity. For planets orbiting these stars, the variability can introduce challenges and complexities that directly influence their climates, atmospheric stability, and overall habitability. One of the most immediate effects of a variable star's changing brightness is the impact on a planet's energy budget. Stars are the primary source of energy for their planets, dictating surface temperatures and driving atmospheric dynamics. When a star brightens, it delivers more energy to its planets, potentially causing temporary or long-term heating of their surfaces and atmospheres. Conversely, when a star dims, less energy reaches the planets, which can lead to cooling. For planets in the habitable zone of a variable star, these fluctuations could result in rapid and unpredictable temperature swings, making it difficult for stable climates to develop. The nature of these fluctuations depends on the type of variable star. Pulsating variables, such as Cepheid variables, change brightness as their outer layers expand and contract. This rhythmic pulsation can cause periodic variations in the amount of energy reaching orbiting planets. In some cases, the changes might be minor, allowing planets to maintain relatively stable conditions. In others, the fluctuations could be so extreme that any surface water on the planet alternates between freezing and evaporating over short periods, disrupting the potential for life. Eruptive variables such as T-Tauri stars present a different challenge. These young stars experience dramatic outbursts of energy and radiation as they go through early stages of stellar evolution. Planets orbiting such stars are exposed to intense stellar winds, bursts of ultraviolet and X-ray radiation, and periods of heightened luminosity. For young planetary systems, these conditions can strip away nascent atmospheres, particularly for smaller planets with weaker gravitational holds. This loss of atmosphere could render planets barren before they have a chance to stabilize and develop conditions suitable for life. Eclipsing binary stars add another layer of complexity. In these systems, two stars orbit each other, and their combined brightness fluctuates as one star passes in front of the other from our perspective. For planets orbiting one or both of these stars, the varying light levels can create erratic patterns of heating and cooling. A planet might experience a prolonged night when its primary star is eclipsed, followed by intense heating when both stars are visible. This uneven energy distribution could result in extreme climate patterns, with some regions of the planet experiencing perpetual freezing, while others are scorched. An atmosphere acts as a buffer, however. When the energy input from the star changes rapidly, the atmosphere may struggle to adapt. During periods of increased stellar brightness, the atmosphere might expand and lose molecules to space, especially if the planet lacks a strong magnetic field to protect it. When the star dims, the atmosphere could collapse inward, altering wind patterns and potentially triggering severe weather events. Intense bursts of ultraviolet and X-ray radiation during bright phases can break apart molecules in the atmosphere, leading to the formation of reactive species like ozone. While ozone can protect a planet's surface from harmful radiation, excessive UV exposure can destroy it just as quickly. The balance between production and destruction of these molecules determines the atmosphere's ability to shield the surface from harmful radiation and maintain stable conditions. On planets without atmospheres, the surface temperature responds immediately to changes in stellar output, creating a landscape that alternates between extreme heat and cold. This could cause the surface to expand and contract, leading to cracking and erosion over time. If the planet has ice or volatile materials on its surface, these substances might evaporate during bright phases and condense again during dim periods, creating dynamic cycles that reshape the planet's surface features. Planets closer to the star experience more intense fluctuations in energy, making them more vulnerable to atmospheric loss and extreme temperature changes. Those farther away are less affected, but may still face challenges if the variability is strong enough. For planets in the habitable zone, even minor fluctuations can tip the delicate balance needed to maintain liquid water, either by causing runaway greenhouse effects or by freezing surface water during dim phases. But variable stars may not entirely preclude the possibility of life on their planets. Some scientists speculate that life could adapt to these fluctuating conditions, particularly if the variability is predictable. For example, organisms might develop mechanisms to survive prolonged periods of darkness or intense radiation. On planets with subsurface oceans or underground habitats, life could remain insulated from the star's variability, relying on geothermal energy or chemical reactions rather than stellar light. Superflares and their legacy on planetary atmospheres. Superflares are powerful eruptions that release immense amounts of energy in a matter of minutes or hours, dwarfing the most intense flares observed on our Sun. For planets orbiting stars prone to superflares, the consequences can be profound. Over time, repeated exposure to these energetic outbursts can strip away gases, alter chemical compositions, and create challenging environments for the development and survival of life. Stellar superflares occur when magnetic fields on the surface of a star become twisted and then suddenly release their stored energy. The result is a massive burst of radiation, often accompanied by charged particles and plasma ejected into space. For planets orbiting close to such stars, the effects of a superflare are direct and unavoidable. High-energy radiation, such as ultraviolet and X-rays, penetrates the upper layers of an atmosphere, breaking apart molecules and creating reactive ions. Proxima Centauri is a prime example of a star with a history of superflares. Proxima b, an exoplanet located within its habitable zone, receives significantly more radiation from its parent star than Earth does from the Sun. Observations of Proxima Centauri have recorded superflares thousands of times more powerful than any solar flare ever observed. These events unleash a torrent of high-energy particles and radiation, creating conditions that could erode the planet's atmosphere over time. The process of atmospheric erosion begins with the interaction of high-energy photons and particles with the outermost layers of the atmosphere. When UV and X-ray radiation strike atmospheric molecules, they can strip away electrons, ionizing the gas. These ions are then vulnerable to being swept away by stellar winds, especially if the planet lacks a strong magnetic field to deflect the incoming particles. Over billions of years, this process can significantly thin or even completely strip an atmosphere, leaving a planet barren and exposed. Proxima b's close proximity to its star exacerbates the problem. Orbiting just 0.05 astronomical units from Proxima Centauri, it is subject to intense stellar winds and frequent flares. Studies suggest that a single superflare could strip away significant portions of its atmosphere if it lacks sufficient protection. While Proxima b may have started with an Earth-like atmosphere, the relentless bombardment from its star raises questions about whether it could have retained enough of it to support life today. Another intriguing system is Gliese 667, a triple star system located about 23 light-years away. One of its stars, Gliese 667c, is a red dwarf with at least 3 known planets in its habitable zone. While not as flare-prone as Proxima Centauri, Gliese 667c still exhibits activity that could impact its planets. Superflares from this star could deliver bursts of radiation capable of altering atmospheric chemistry, creating temporary or permanent changes in the climate and habitability of its planets. For planets in the habitable zone of such stars, the timing and frequency of superflares are critical factors. A single superflare might cause localized damage, such as the temporary depletion of ozone layers or the loss of lighter gases like hydrogen. However, if superflares occur frequently, their cumulative effects can be far more devastating. Repeated flaring events could deplete an atmosphere entirely, especially if the planet is unable to replenish its lost gases through volcanic activity or other geological processes. Thick, dense atmospheres, rich in heavy molecules like carbon dioxide, may be more resistant to erosion than thinner, hydrogen-rich ones. For example, Venus's dense atmosphere has proven remarkably resilient despite the intense solar radiation it receives. If exoplanets orbiting stars like Proxima Centauri or Gliese 667c possess similarly robust atmospheres, they might retain some protection against the effects of superflares. The long-term legacy of superflares also includes their potential to shape the chemistry of an atmosphere in ways that could either hinder or promote the development of life. High-energy radiation can break apart stable molecules like water or carbon dioxide, creating reactive species such as hydroxyl radicals or free oxygen atoms. These reactive molecules can drive complex chemical reactions, potentially leading to the formation of organic compounds. On the other hand, excessive radiation can destroy existing organic molecules, creating a harsh environment for any emerging life. For planets with subsurface oceans or thick ice layers, the surface and atmosphere absorb the brunt of the radiation, while the subsurface environment remains relatively insulated. Life in these hidden oceans could be shielded from the harmful effects of superflares, relying on geothermal energy or chemical reactions rather than sunlight for sustenance. The study of superflares and their effects also has implications for understanding the early history of our own solar system. The young Sun likely produced more frequent and intense flares during its early stages, potentially influencing the atmospheres of Earth, Mars, and Venus. By studying exoplanets around flare-prone stars, scientists can gain insights into the processes that shaped the atmospheres of terrestrial planets in our solar system and beyond. The role of tidal locking in determining habitability. Tidal locking is a phenomenon that occurs when a planet's rotation period matches its orbital period, causing one side of the planet to perpetually face its star, while the other side remains in constant darkness. This effect is common for planets orbiting close to their stars, especially around red dwarfs, where the habitable zone is so close that gravitational forces between the star and the planet become dominant over time. One of the most striking consequences of tidal locking is the stark contrast in conditions between the day side and the night side of the planet. The side facing the star is constantly bathed in light and heat, potentially creating scorching temperatures. Meanwhile, the night side is shrouded in eternal darkness, leading to freezing conditions. This extreme dichotomy could result in a planet that is seemingly inhospitable, but the reality is more nuanced. On a planet with a thick and dynamic atmosphere, winds and convection currents can transport heat from the day side to the night side, reducing temperature extremes. This redistribution could create a more temperate twilight zone along the terminator, the boundary between the day and night sides. In this region, conditions might be stable enough to allow for the presence of liquid water, a critical ingredient for life as we know it. The strength and efficiency of this heat transfer depend on the composition, density, and dynamics of the planet's atmosphere. On a tidally locked world, water might accumulate on the night side in the form of ice, where the cold temperatures prevent it from evaporating. Meanwhile, the day side could experience significant evaporation due to constant heating, potentially creating a cycle where water vapor is transported through the atmosphere and redeposited as ice on the night side. This process could result in unique weather patterns and climate systems that differ significantly from those on Earth. A strong magnetic field would help protect the atmosphere from stellar winds and radiation, increasing the chances of maintaining a stable environment. Without this protection, the atmosphere could erode over time, leaving the planet exposed to harsh space conditions. Tidally locked planets may have slower rotations, which could reduce the effectiveness of their magnetic dynamo and make them more vulnerable to atmospheric loss. Despite the challenges, tidal locking may offer some surprising advantages for habitability. The stable lighting conditions on the day side could support the growth of photosynthetic organisms if they exist, providing a steady source of energy. Additionally, the lack of a day-night cycle could create a predictable environment for life to adapt to, potentially leading to unique evolutionary pathways. Organisms might develop specialized adaptations to thrive in the constant light of the day side, or the perpetual darkness of the night side. Models suggest that even with minimal atmospheric circulation, the twilight zone along the terminator could maintain moderate temperatures suitable for liquid water. The extent of this habitable region depends on factors such as the planet's albedo or reflectivity and the composition of its atmosphere. High albedo surfaces, such as ice or clouds, reflect more sunlight and could cool the planet, while a thicker atmosphere with greenhouse gases might trap heat and expand the habitable zone. The study of tidally locked planets is not limited to exoplanets. In our solar system, the Moon is a tidally locked body, always showing the same face to Earth. While it lacks an atmosphere and is not habitable, the Moon provides a valuable analogue for understanding the dynamics of tidal locking and its effects on a celestial body's environment. Observations of the Moon's surface and thermal properties help refine models that can be applied to tidally locked exoplanets. Planetary climate extremes on 55, Cancri E. 55 Cancri E, located a bit beyond the 10 parsec limit, but still at a relatively close 40 light-years away in the constellation Cancer, stands out as one of the most extreme exoplanets discovered. This super-Earth, roughly twice the size of our planet and about 8 times its mass, orbits its star at a breathtakingly close distance. Completing a single orbit in just 18 hours, it lies far within the region where most rocky planets would be consumed by their stars. The conditions on 55 Cancri E are nothing short of extraordinary, with surface temperatures that soar far beyond anything experienced on Earth, a potentially molten landscape, and intriguing possibilities about its composition. The intense heat on 55 Cancri E is one of its most striking features. Being so close to its host star, a yellow dwarf similar to our Sun but slightly cooler, the planet's day side experiences temperatures exceeding 2,400 degrees Celsius, or about 4,300 degrees Fahrenheit. This is hot enough to melt most metals and keep much of the surface in a molten state. The night side, though cooler, still endures searing temperatures of around 1,200 degrees Celsius, or about 2,200 degrees Fahrenheit. This stark contrast between the day and night sides raises questions about the planet's atmosphere, or lack thereof, and how heat is distributed across its surface. Some observations suggest that 55 Cancri E may have a thin or patchy atmosphere, while others propose it might lack an atmosphere altogether. If an atmosphere exists, it would need to withstand the intense stellar radiation and heat. It might consist of heavy gases like carbon dioxide or sulfur dioxide, substances that can endure high temperatures without breaking apart. However, if the planet has no atmosphere, the heat from its star would directly strike the day side, creating an even more dramatic temperature gradient. The absence of an atmosphere would also mean no protection from the relentless bombardment of stellar winds and radiation. Observations hint at the possibility of vast oceans of lava covering significant portions of the planet. These lava flows could result from volcanic activity, driven by the planet's intense internal heat and tidal forces from its close proximity to its star. Tidal forces stretch and compress the planet's interior, generating heat through friction and potentially fueling widespread volcanism. Such activity could continually reshape the surface, with new lava flows solidifying and then melting again as conditions fluctuate. Volcanism on 55 Cancri E might also create dramatic plumes of gas and particles that rise into the atmosphere. These eruptions could briefly alter the planet's albedo, or reflectivity, by spreading clouds of volcanic ash and gas across the surface. However, given the extreme temperatures, Any volcanic gases released would likely dissipate quickly or condense back onto the surface as the planet rotates. The interplay between volcanism, heat, and the potential atmosphere adds complexity to understanding this alien world. The idea that 55 Cancri E could be a carbon planet adds another fascinating dimension to its story. Carbon planets are hypothetical worlds rich in carbon rather than oxygen, unlike Earth. If 55 Cancri E formed in a region of its star system with a high carbon-to-oxygen ratio, its surface might be dominated by graphite and diamond instead of silicate rocks. Under extreme pressure, carbon could crystallize into diamond, potentially creating a landscape glittering with solid carbon structures. If 55 Cancri E is indeed a carbon planet, its molten surface might contain liquid carbon compounds, forming lava-like rivers of molten carbon. The planet's interior could also differ significantly from Earth's, with layers of graphite and diamond rather than the silicate mantle and iron core familiar to us. Such a composition would not only make 55 Cancri E unique, but also provide valuable insights into how planets form and evolve under different chemical conditions. The proximity of 55 Cancri E to its star also affects its long-term stability. Over time, the intense radiation and stellar winds could strip away any atmosphere the planet might have had, leaving it exposed to the harsh conditions of space. This process, known as atmospheric escape, is more pronounced for planets orbiting close to their stars. If 55 Cancri E once had a thicker atmosphere, it might have been gradually eroded by the unrelenting energy of its star, leaving behind the extreme environment observed today. High temperatures and pressures could drive unusual chemical reactions, creating compounds that don't exist on Earth. These compounds might form on the surface, in the atmosphere, if present, or within the planet's molten interior. Studying such chemistry, even from afar, could expand our understanding of how elements behave under extreme conditions and provide clues about the diversity of planetary environments. By studying this extreme world, scientists can test theories about planet formation, composition, and evolution. Its close proximity to its star provides a natural laboratory for understanding how stellar radiation and tidal forces shape planetary environments. Observations of 55 Cancri E have already challenged assumptions about what types of planets can survive in such close orbits, suggesting that planets may be more resilient than previously thought. The resonance phenomenon: how planets like Luyten b stay in sync. Orbital resonances shape the movement and interactions of celestial bodies over millions of years. These resonances occur when the orbital periods of two or more objects are related by a simple ratio, like 2, 1 or 3, 2. This synchrony can have a profound influence on the stability of orbits, the evolution of climates, and even the habitability of planets. Luyten b orbits Luyten's star in a relatively tight orbit. With a year lasting just over 18 Earth days, it lies well within the habitable zone of this dim red dwarf. Its location suggests the potential for liquid water, assuming the planet has a stable atmosphere. But the influence of resonance could play a key role in maintaining or disrupting that stability. If Luyten b shares its system with other planets, their gravitational interactions might lock them into specific orbital relationships. These relationships could help regulate the climate on Luyten b, but they might also introduce challenges depending on the nature of the resonance. In systems where resonance stabilizes orbits, the gravitational nudges between planets occur at regular intervals, preventing chaotic interactions that might otherwise lead to dramatic shifts in orbit. This stability can be crucial for a planet like Luyten b, as consistent orbital parameters allow for predictable seasonal cycles and climate patterns. Without resonance, gravitational perturbations from neighboring planets could cause variations in Luyten b's orbit, potentially pulling it closer to or farther from its star. Such shifts could result in significant changes in temperature, threatening the presence of liquid water and any life that might rely on it. In tightly packed planetary systems, These forces can have a substantial impact on a planet's interior, potentially driving geological activity. For Luyten b, tidal heating might help maintain a warm subsurface environment, even if surface temperatures fluctuate. This could create a scenario where liquid water exists beneath a frozen crust, similar to subsurface oceans observed on moons like Europa and Enceladus in our solar system. If resonance amplifies tidal heating, it could enhance these subsurface environments, providing a stable refuge for life. A stable orbit ensures consistent energy input from the star, allowing the atmosphere to develop equilibrium patterns over time. However, resonance-induced variations could disrupt these patterns, creating periods of heating and cooling that test the resilience of the atmosphere. If Luyten b's atmosphere is dense and robust, it might buffer these changes, maintaining conditions suitable for habitability. On the other hand, a thin or weak atmosphere might struggle to cope, leading to extreme temperature swings and reduced habitability. If Luyten b is part of a multi-planet system, the specific configuration of these planets could reveal much about how the system formed and evolved. For example, planets in resonance often migrate into their current positions during the early stages of the system's development. This migration process can influence the distribution of material within the system, affecting the composition and size of the planets. If Luyten b shares a resonance with a neighboring planet, it might provide clues about the history of the system and the forces that shaped it. Observing resonance in action is challenging, especially for distant systems like Luyten's star. Scientists rely on precise measurements of planetary orbits to detect these relationships, often using methods like transit timing variations. By studying the timing of Luyten b's transits across its star, astronomers can identify subtle deviations caused by gravitational interactions with other planets. These deviations can reveal the presence of resonance and help determine its impact on Luyten b's orbit and climate. One of the most famous examples of resonance in our solar system is the relationship between Jupiter's moons Io, Europa, and Ganymede. These moons are locked in a 4-2-1 resonance, meaning that for every 4 orbits Io completes, Europa completes 2 and Ganymede completes 1. This resonance maintains the stability of their orbits while driving tidal heating within their interiors. For Luyten b, a similar resonance with a neighboring planet could have comparable effects, maintaining orbital stability while influencing geological and atmospheric processes. If Luyten b is part of a resonant chain, identifying one planet can provide hints about the presence and location of others. This approach has been used successfully in other systems, where the discovery of one planet led to the detection of multiple others in resonance. In some cases, resonance can destabilize a planet's climate, particularly if the gravitational interactions are strong enough to induce significant variations in orbit. For Luyten b, a resonance that introduces eccentricity, an elliptical orbit, could result in extreme temperature fluctuations. During periods when the planet is closer to its star, it might experience intense heating, while greater distances could lead to freezing conditions. Such a scenario would make it difficult for life to establish a foothold, as organisms would need to adapt to constantly changing environments. The resonance phenomenon highlights the delicate balance that governs planetary systems. For Luyten b, the presence or absence of resonance could be a defining factor in its habitability. If resonance stabilizes its orbit and climate, it might enhance the planet's potential to support life. However, if resonance introduces variability, it could create challenges that test the limits of habitability. Water worlds, oceans beyond imagination. Water worlds, planets entirely or almost entirely covered by vast oceans, represent some of the richest possibilities in the search for habitable exoplanets. The concept of water worlds is rooted in the discovery of exoplanets, with densities lower than rocky planets like Earth, but higher than gas giants. These intermediate densities suggest the presence of significant amounts of water, possibly forming thick oceans. Some of the planets of the TRAPPIST-1 system, located about 40 light-years away, may be water worlds. Unlike Earth, where water covers about 70% of the surface, but accounts for only a thin layer relative to the planet's total volume, water worlds could have oceans hundreds or even thousands of kilometers deep. Beneath these oceans, a dense layer of high-pressure ice might form due to the immense weight of the water above. The climates of water worlds are likely to be drastically different from those of terrestrial planets. With no land masses to break up ocean currents or provide anchors for weather patterns, the entire planet could be subject to powerful, unbroken storms. Winds might sweep across the surface, creating waves far larger than anything seen on Earth. Ocean currents, driven by temperature differences between the equator and the poles, could circulate heat more evenly, potentially stabilizing the planet's climate. However, without land to moderate the movement of heat, these currents might also create extreme temperature contrasts in different regions of the ocean. On Earth, plate tectonics play a crucial role in recycling carbon dioxide through volcanic activity and maintaining a stable climate over geological timescales. On a water world, the lack of exposed land might inhibit these processes, leading to questions about how the planet regulates its atmosphere. One possibility is that chemical reactions between the ocean and the sea floor could serve as an alternative mechanism for maintaining a stable climate. These reactions might involve the cycling of carbon and other elements between the ocean and the planet's rocky interior. On Earth, land provides a diversity of habitats and a source of nutrients for marine life through runoff and erosion. On a water world, life would have to rely entirely on the resources available in the ocean. This could lead to ecosystems dominated by microorganisms, similar to the deep-sea ecosystems on Earth that thrive around hydrothermal vents. These vents, which release heat and minerals from the seafloor, could provide the energy needed for life to flourish in the absence of sunlight. If a water world orbits within its star's habitable zone, the surface temperature could allow for liquid water, creating an environment where life might emerge. However, the depth of the ocean and the presence of a high-pressure ice layer could isolate the ocean from the planet's interior. This isolation might limit the exchange of nutrients and energy between the seafloor and the surface, potentially restricting the diversity and complexity of life. Alternatively, if the ice layer is thin enough to allow for some interaction, it could create pockets of more dynamic environments where life could thrive. A thick atmosphere, rich in greenhouse gases, could trap heat and prevent the ocean from freezing over, even at the poles. However, if the atmosphere is too thick, it could create a runaway greenhouse effect, boiling away the water and leaving behind a desolate, uninhabitable world. Balancing these factors is a delicate process, and the outcome depends on the planet's initial conditions and its evolutionary history. Some water worlds might exist beyond the traditional habitable zone, where surface temperatures are too cold for liquid water. In these cases, the ocean could be covered by a thick layer of ice, similar to the icy moons of our solar system, such as Europa and Enceladus. Beneath this ice, the ocean could remain liquid due to heat generated by the planet's interior, either from radioactive decay or tidal interactions with a nearby star or other planets. On Earth, water is a fundamental requirement for life, and the discovery of life in extreme environments, such as deep-sea vents and subglacial lakes, suggests that life could potentially adapt to the conditions on water worlds. The lack of land might limit the complexity of life, but it could also create opportunities for unique adaptations. For example, organisms might develop ways to harness the energy of ocean currents or the chemical gradients created by interactions between the ocean and the sea floor. In our solar system, Earth is the only planet with a significant amount of liquid water on its surface. The discovery of water worlds elsewhere suggests that they might be more common than previously thought, raising questions about why Earth ended up with its particular mix of land and water. Understanding the factors that lead to the formation of water worlds can provide insights into the processes that shape planetary systems and the potential for life in the universe. Epsilon Indi Ab, a massive planet orbiting a binary star system. Epsilon Indi Ab is a fascinating gas giant located in a complex trinary star system about 12 light-years away in the constellation Indus. This planet, with a mass approximately 6 times that of Jupiter, orbits its primary star, Epsilon Indi A, at a distance of 11.55 astronomical units, or AU. It takes around 45.2 Earth years to complete a single orbit. This distance places it far from its host star, making it exceptionally cold. The Epsilon Indi system consists of 3 stars: Epsilon Indi A, the main sequence star hosting the planet, and 2 brown dwarfs, Epsilon Indi Ab and BB. These brown dwarfs orbit each other and collectively revolve around Epsilon Indi A at a much greater distance. The presence of these additional stellar companions creates a unique environment where gravitational interactions can influence the planet's orbit and overall stability. While the planet primarily orbits Epsilon Indi A, the distant pull of the brown dwarf companions introduces complexities to its motion. Over long timescales, this interaction could potentially alter the planet's orbit, leading to slight variations in its distance from the star. These shifts, though subtle, can have a significant impact on the planet's climate and any potential satellites it might host. The combined light from the 3 stars complicates direct observations of the planet. The light from Epsilon Indi A dominates, but the brown dwarfs also contribute faint emissions, which can obscure the already dim signals from the planet itself. Advanced techniques such as direct imaging are necessary to isolate the planet's light from the background noise. In this regard, JWST has played a pivotal role. The direct imaging of Epsilon Indi Ab using the JWST is a landmark achievement in exoplanet science. Unlike traditional detection methods, such as radial velocity or transit techniques, direct imaging captures the light emitted or reflected by the planet itself. This approach provides a wealth of information about the planet's physical and atmospheric properties. For Epsilon Indi Ab, the JWST's imaging has not only confirmed its existence, but also offered insights into its cold environment. The measured temperature of approximately 2 degrees Celsius is particularly intriguing and makes it one of the coldest exoplanets to be directly detected. At 11.55 AU, it receives significantly less stellar radiation than planets closer to their stars. This places it well outside the traditional habitable zone, where liquid water might exist on the surface. However, its low temperature also makes it an excellent candidate for studying atmospheric and surface properties without the interference of intense stellar heat. Scientists can use these observations to compare it with similar gas giants in our own solar system like Jupiter and Saturn. If Epsilon Indi Ab has moons, they could be interesting targets for future study, especially if they are large enough to sustain atmospheres. The gravitational stability provided by such a massive planet might shield these moons from some of the disruptions caused by the brown dwarf companions, allowing them to maintain relatively stable orbits. In systems with multiple stars, the process of planet formation can be more chaotic than in single-star systems like our own. The presence of additional stellar companions can influence the distribution of gas and dust in the protoplanetary disk, affecting where and how planets form. Epsilon Indi Ab's existence suggests that even in the presence of these complicating factors, massive planets can form and survive over billions of years. By comparing it to gas giants in single-star systems, scientists can identify patterns and differences that reveal how the presence of multiple stars shapes planetary development. For example, does the gravitational influence of the brown dwarfs make the system more or less likely to host additional planets? And how does the planet's orbit compare to those of gas giants in simpler systems? These questions are crucial for piecing together the puzzle of planetary formation. The discovery of Epsilon Indi Ab shows that massive planets can thrive even in the dynamic environments of trinary systems. Its relatively stable orbit, despite the gravitational pull of the brown dwarfs, highlights the resilience of planetary systems under complex conditions. The data collected from Epsilon Indi Ab will also inform the search for similar planets in other multi-star systems. By studying its characteristics, astronomers can refine their models and improve their ability to detect and characterize planets in these challenging environments. This knowledge will be valuable as telescopes become more advanced, enabling the discovery of even more distant and complex systems. The day-night divide on tidally locked nearby exoplanets. The constant day and night divide on tidally locked worlds creates two vastly different environments on a single planet. The terminator zone could have a stable climate, where temperatures are moderate enough to allow liquid water to exist, provided other conditions, such as atmospheric composition and pressure, are suitable. On a planet with an atmosphere capable of redistributing heat, the day side might have dense cloud cover. These clouds, formed by the intense evaporation of any surface water or atmospheric gases, could reflect much of the incoming starlight back into space, preventing the surface from overheating. Meanwhile, the night side might accumulate atmospheric gases that condense into ice or snow, creating a stark contrast between the two hemispheres. Such a planet would likely have unique weather patterns, with strong winds flowing from the hot day side to the cold night side, carrying heat, moisture, and other atmospheric components in a continuous cycle. On the day side, organisms would need to cope with relentless heat and radiation from the star. Life here might evolve protective mechanisms, such as reflective surfaces or burrowing behaviors, to shield against the harsh conditions. Alternatively, organisms could thrive in microhabitats, such as shaded areas created by rocky outcrops or within cracks and crevices that provide refuge from the sun's intensity. Without sunlight, any potential life on the night side would need to rely on alternative energy sources. This could include geothermal heat or chemical energy derived from interactions between minerals and water. Subsurface ecosystems might be possible on the night side, especially if the planet retains some level of geological activity. The terminator zone, with its milder conditions, might be the most promising region for life on a tidally locked planet. Here, organisms could take advantage of a stable environment where liquid water is more likely to exist. The twilight zone could host unique ecosystems adapted to the dim light conditions, with life forms developing photosynthetic processes optimized for low light levels. The interplay between the heat of the day side and the cold of the night side could also create dynamic weather systems, such as rain or snow, that provide a steady supply of water and nutrients to this region. On Earth, life is accustomed to cycles of day and night, which drive biological rhythms and behaviors. On a tidally locked planet, these cycles would not exist. Instead, life might adapt to the planet's unique conditions by developing entirely new strategies for survival. For example, mobile organisms could migrate between the terminator zone and the more extreme regions, taking advantage of resources found in different areas while avoiding the worst of the heat or cold. Alternatively, life could remain stationary but develop highly specialized adaptations to its local environment. On the day side, organisms might evolve reflective or heat-resistant structures, while those on the night side could develop anti-freeze-like compounds to survive the freezing temperatures. The terminator zone might host organisms capable of exploiting both environments, using the energy and resources from the day side while avoiding the coldest regions of the night side. The absence of a day-night cycle could influence everything from the evolution of timekeeping systems to the development of agriculture and energy production. Civilizations on the day side might harness solar energy, while those on the night side could rely on geothermal or chemical energy sources. The terminator zone, with its moderate climate, might provide the best conditions for the growth of complex societies, offering a stable environment with access to resources from both hemispheres. What these planets teach us about our solar system. The study of nearby exoplanets provides a unique opportunity to reflect on our own solar system. By comparing these distant worlds to the planets we know so well, we can uncover similarities that hint at universal processes in planetary formation and evolution. At the same time, the differences challenge us to think more broadly about the diversity of planetary systems and the factors that make each one unique. One similarity is the presence of rocky planets close to their stars, much like Mercury, Venus, Earth and Mars in our solar system. Worlds such as Proxima b and Teegarden b are rocky planets orbiting within the habitable zones of their red dwarf stars. These planets remind us of Earth, at least in terms of size and mass, and their positions within their systems raise the same fundamental questions about habitability and the conditions needed to support life. However, these exoplanets also show key differences. Unlike Earth, many of them orbit much closer to their stars, often completing a full revolution in just a few days. This proximity subjects them to intense stellar radiation and gravitational forces that shape them in ways unlike anything in our solar system. Gas giants like Jupiter and Saturn also have their counterparts. Hot Jupiters, which are gas giants that orbit very close to their stars, are particularly fascinating because they challenge our understanding of how planets migrate. In our solar system, Jupiter and Saturn formed far from the Sun, where temperatures were low enough for gases to condense. The presence of hot Jupiters around other stars suggests that planetary migration is more complex than we thought. Observations of these distant worlds have revealed exotic features like high-altitude clouds made of silicates or metals, as well as extreme temperature variations between their day and night sides. While Jupiter and Saturn are not exposed to such intense radiation, studying hot Jupiters provides a framework for understanding how atmospheres respond to heat and pressure, offering insights into the more temperate conditions in our own solar system. On Europa and Enceladus, jets of water and other materials erupt from cracks in the ice, providing direct evidence of subsurface activity. If similar phenomena exist on icy exoplanets, they could offer a way to study these distant worlds without needing to land on them. Observing such activity from Earth would require extremely sensitive instruments, but the possibility underscores the connections between our solar system and the broader universe. Many exoplanets, like Wolf 1061c, may have undergone runaway greenhouse effects similar to Venus. By studying the atmospheres of these planets, scientists can test models of atmospheric loss and climate change that are also relevant to Venus. Observations of high levels of carbon dioxide on an exoplanet could support theories about how volcanic activity and solar radiation contributed to Venus's transformation into a hot, uninhabitable world. The stability of our planet's orbits, the relatively low level of solar activity, and the protective presence of Jupiter, all these factors have contributed to Earth's ability to sustain life. Nearby exoplanets often lack one or more of these features, leading to more extreme conditions. For example, the frequent flares of red dwarf stars can strip away atmospheres or bombard planets with radiation, challenges that Earth has not faced to the same extent. By studying these differences, we can appreciate the delicate balance that has allowed life to thrive here. At the same time, exoplanets offer a glimpse into what might have been. If Jupiter had migrated inward, as many hot Jupiters have, it could have disrupted the formation of Earth or pushed it into a less favorable orbit. Similarly, if Earth had been slightly closer to or farther from the Sun, its climate might have resembled that of Venus or Mars. Their study serves as a reminder of the many factors that shape a planet's destiny and the interconnectedness of planetary systems. By comparing nearby exoplanets to the planets in our solar system, we can see both the universality of certain processes and the unique circumstances that have shaped our cosmic neighborhood. Each discovery adds to a growing tapestry of knowledge, connecting the dots between distant worlds and the one we call home. The role of the James Webb Space Telescope in exoplanet discovery. The James Webb Space Telescope, often called JWST, represents a significant leap forward in humanity's ability to study the universe. It is a successor to the Hubble Space Telescope, but with far more advanced instruments, designed specifically to see into the depths of space with unprecedented clarity. While its mission spans a wide range of astronomical topics, from the earliest galaxies to the birth of stars, one of its most exciting capabilities lies in its potential to study exoplanets. For planets orbiting stars near our solar system, JWST offers tools that could uncover the secrets of their atmospheres, climates, and even the possibility of life. One of the telescope's key strengths is its ability to observe in the infrared spectrum. Unlike visible light, which is what our eyes can see, infrared light reveals details that would otherwise remain hidden. This capability is particularly important for studying exoplanets because their host stars often outshine them significantly in visible light. In infrared, the faint glow of an exoplanet can stand out more clearly, allowing scientists to analyze it separately from the overwhelming brightness of its star. JWST's instruments are specifically designed to detect this faint light and extract as much information as possible. When it comes to exoplanet research, one of the most valuable techniques is transit spectroscopy, which involves observing a planet as it passes in front of its star. During the transit, some of the starlight passes through the planet's atmosphere before reaching JWST. The atmosphere leaves a signature in the light, altering it in ways that depend on the gases and particles present. By analyzing this light, scientists can determine the composition of the atmosphere, identifying elements like oxygen, carbon dioxide, methane, and water vapor. JWST's instruments are finely tuned for this type of analysis. The near-infrared spectrograph, or NIRSpec, and the mid-infrared instrument, or MIRI, are two key components that allow it to break down light into its individual wavelengths. This detailed view makes it possible to detect even small amounts of specific gases, which is crucial for understanding the atmospheres of distant planets. For example, the presence of water vapor could suggest that a planet has liquid water, while the detection of methane and oxygen together might hint at biological processes. One of the challenges in studying exoplanet atmospheres is that they are incredibly thin compared to the size of the planets themselves. This means the changes in starlight caused by the atmosphere are often subtle, requiring instruments with extreme precision. JWST's ability to detect these minute differences is a game-changer. It can not only identify the major components of an atmosphere, but also look for trace gases that might have significant implications for habitability. Another advantage is its ability to observe exoplanets at different times and in various conditions. For example, it can study a planet during its transit, but it can also observe the planet after it has moved out of alignment with its star. By comparing the light from the star alone with the light from the star-planet system, scientists can gather more data about the planet's properties. This approach, known as secondary eclipse spectroscopy, provides insights into the temperature of the planet's atmosphere and its potential heat distribution. By studying a variety of planets across different types of stars, scientists can start to see patterns in how atmospheres form and evolve. This could reveal how factors like stellar radiation, planetary mass, and orbital distance influence the ability of a planet to retain an atmosphere. One of the telescope's most anticipated targets is the TRAPPIST-1 system, a collection of 7 Earth-sized planets orbiting a red dwarf star about 40 light-years away. Several of these planets are located in the star's habitable zone, where temperatures might allow liquid water to exist. JWST's instruments are perfectly suited to study these worlds, potentially determining whether they have atmospheres and what those atmospheres are made of. Given the proximity of the TRAPPIST-1 system and the unique configuration of its planets, it is an ideal testing ground for JWST's capabilities. JWST will also focus on planets around stars like Proxima Centauri and Teegarden's star. These stars are much closer to Earth, allowing for more detailed observations. For planets like Proxima b, which orbits close to its star, JWST could help determine whether the atmosphere has survived the intense radiation from stellar flares. By measuring the composition and thickness of the atmosphere, scientists can assess whether the planet might still have conditions suitable for life. One of the most exciting possibilities is the detection of biosignatures, which are specific gases or combinations of gases that might indicate the presence of life. For instance, a high concentration of oxygen alongside methane would be difficult to explain through purely geological processes and might point to biological activity. JWST's sensitivity to infrared light makes it well suited to search for these signals, especially on planets with Earth-like conditions. While JWST is an incredibly powerful tool, it is not without its limitations. For one, it cannot directly image most exoplanets, as they are too small and faint compared to their host stars. For that, even larger telescopes will need to be designed. Instead, it relies on indirect methods like spectroscopy to gather data. Additionally, its exoplanet observations are limited to relatively nearby systems, as the light from more planets becomes too weak to analyze in detail. Despite these challenges, JWST represents a monumental step forward in our ability to study worlds beyond our solar system, and the discoveries it makes will shape the direction of exoplanet research for decades to come, inspiring future missions and advancing our understanding of the universe. Can we detect biosignatures from 10 parsecs away? Detecting biosignatures from 10 parsecs away presents a unique set of challenges and opportunities. Biosignatures are chemical or physical indicators that could point to the presence of life, whether past or present. On Earth, life significantly influences the composition of our atmosphere, producing gases like oxygen, methane, and nitrous oxide in quantities that would be difficult to explain without biological activity. When light from a star passes through a planet's atmosphere, some of it gets absorbed or scattered by the gases and particles in that atmosphere. The specific wavelengths of light absorbed depend on the chemical composition of the atmosphere. For example, oxygen absorbs light at distinct wavelengths, as do methane, carbon dioxide, and water vapor. By studying these absorption patterns, scientists can infer which gases are present in the atmosphere of a distant planet. One of the primary methods for detecting biosignatures is transit spectroscopy. During the transit, some of the starlight filters through the planet's atmosphere, picking up chemical signatures along the way. Telescopes equipped with spectrometers can analyze this filtered light, breaking it down into its component wavelengths to create a spectrum. Each gas in the atmosphere leaves a unique fingerprint on this spectrum. Detecting biosignatures like oxygen and methane, however, is not straightforward. For one, the signals are incredibly faint. Even the most advanced telescopes struggle to pick out these subtle changes in light, especially when dealing with planets that are so far away. 10 parsecs might seem close on a cosmic scale, but it's still an immense distance. And the light reaching Earth-based or space-based telescopes is often dim and distorted. To overcome this, scientists rely on highly sensitive instruments designed specifically for exoplanet research. Another challenge lies in interpreting the data. Oxygen and methane, for instance, are often considered promising biosignatures because they are produced in large quantities by life on Earth. Plants, algae, and cyanobacteria release oxygen through photosynthesis, while many microbes produce methane as a byproduct of their metabolism. On a distant planet, the simultaneous detection of oxygen and methane could be a strong indicator of life because these gases tend to react with each other and would not coexist in significant amounts without being constantly replenished. However, non-biological processes can also produce these gases. Volcanic activity, for example, can release methane, and oxygen might result from the breakdown of water molecules by ultraviolet light. To determine whether these gases are of biological origin, scientists need to consider the broader context of the planet. This includes its temperature, pressure, and proximity to its star, as well as the presence of other gases that might provide additional clues. For instance, a planet with high levels of methane but no carbon dioxide might raise questions about the source of the methane, as volcanic activity would typically produce both gases. One way is detecting a combination of gases that are out of equilibrium. On Earth, the presence of oxygen and methane together is a sign of life because these gases react with each other and would not persist without biological processes continuously replenishing them. A similar imbalance on a distant planet could point to the presence of life, though it would still require careful analysis to rule out non-biological explanations. Direct imaging is useful for studying planets that do not transit their stars or are located far enough from their stars to be seen as separate points of light. It requires extremely precise instruments to block out the overwhelming brightness of the star and reveal the much fainter light reflected by the planet. Once the planet's light is isolated, it can be analyzed for signs of atmospheric gases and surface features. Future telescopes, like the Extremely Large Telescope and the Habitable Worlds Observatory, are expected to push the boundaries of direct imaging. These instruments will have the sensitivity and resolution needed to study Earth-sized planets around nearby stars, potentially detecting biosignatures from distances of 10 parsecs or more. They will also be able to measure the polarization of light reflected by a planet, which can provide additional information about its atmosphere and surface. For example, polarized light might indicate the presence of clouds, oceans, or even vegetation. In addition to telescopes, scientists are developing models to simulate the atmospheres of distant planets and predict what kinds of biosignatures might be detectable. These models take into account factors like the planet's size, orbit, and the type of star it orbits. Red dwarf stars, for example, are cooler and dimmer, which means their habitable zones are closer in. Planets in these zones might receive more intense stellar radiation, which could affect the stability of their atmospheres and the types of biosignatures that can form. Flares and ultraviolet radiation can strip away a planet's atmosphere or alter its chemical composition, potentially masking or destroying biosignatures. On the other hand, some models suggest that certain gases, like methane, might be more abundant on planets around red dwarfs due to enhanced photochemical reactions. Understanding these processes is crucial for interpreting the data collected by telescopes. Laser propulsion and the prospect of interstellar probes. The idea of sending small, fast probes to nearby stars has long captured the imagination of scientists and engineers. These interstellar missions, though ambitious, are becoming increasingly plausible with advances in technology. At the heart of these plans is the concept of laser propulsion, a technique that could enable probes to travel at a significant fraction of the speed of light. This method could allow humanity to explore planets around nearby stars like Proxima Centauri or Luyten's star within a human lifetime, offering the potential for direct observations that are currently impossible with telescopes alone. Laser propulsion relies on a ground or space-based laser system to propel lightweight spacecraft. The principle is relatively straightforward. A powerful laser beam is directed at a reflective sail attached to the probe. As photons from the laser strike the sail, they transfer momentum, pushing the spacecraft forward. This method eliminates the need for onboard fuel, significantly reducing the mass of the spacecraft and enabling it to achieve much higher speeds than conventional propulsion systems. One of the most prominent projects exploring this concept is Breakthrough Starshot, an initiative launched in 2016. The goal of Starshot is to develop and deploy small wafer-sized probes called star chips, each equipped with cameras, sensors, communication devices, and a reflective sail. These probes would be propelled by a laser array on Earth, potentially reaching speeds of up to 20% the speed of light. At such velocities, a probe could reach Proxima Centauri, our closest stellar neighbor, at 4.24 light-years away in just over 20 years. The potential scientific returns from such a mission are enormous. A probe traveling to Proxima Centauri could capture high-resolution images of its planets, including Proxima b, a potentially habitable exoplanet. It could also analyze the composition of the planet's atmosphere, detect magnetic fields, and search for signs of water or other indicators of habitability. These observations would provide an unprecedented level of detail about a distant world, far surpassing what is possible with current telescopes. Despite its promise, laser propulsion faces significant technical challenges. One of the primary obstacles is the development of a laser array powerful enough to propel the probes. The envisioned system for breakthrough starshot would require a laser array with a total output of 100 gigawatts, equivalent to the peak power demand of a large city. Such a system would need to be highly efficient and capable of focusing its energy precisely over vast distances. The sail must be extremely lightweight, yet durable enough to withstand the intense pressure of the laser beam. It also needs to remain stable and aligned during acceleration, which could involve forces thousands of times stronger than Earth's gravity. Materials science plays a critical role here, with researchers exploring advanced materials like graphene and metamaterials to create sails that meet these demanding requirements. Communication with the probes is another hurdle. At a distance of several light-years, even the smallest signals would be incredibly weak. Engineers are exploring ways to use lasers for communication, taking advantage of their narrow beams and high intensity to transmit data back to Earth. However, this requires precise targeting and timing, as the probes will be moving at extremely high speeds relative to Earth. Traveling at a significant fraction of the speed of light, the probes would encounter interstellar particles with enormous energy, potentially damaging their components. Shielding the probes without adding significant weight is a complex problem that researchers are working to solve. The success of a laser-propelled interstellar mission would depend on rigorous testing and incremental development. Early prototypes would likely be tested within our solar system, targeting nearby planets or asteroids to validate the technology. These missions could provide valuable data and pave the way for future interstellar endeavors. While the challenges are daunting, the potential rewards justify the effort. Interstellar probes could transform our understanding of the universe, providing direct observations of planets around other stars. They could help answer fundamental questions about the prevalence of habitable worlds and the potential for life beyond Earth. In the longer term, they could even lay the groundwork for human exploration of other star systems, demonstrating the feasibility of interstellar travel and inspiring new generations of scientists and engineers. In addition to breakthrough starshot, other concepts for interstellar probes are being explored. Some involve hybrid propulsion systems that combine laser propulsion with other methods, such as ion thrusters or nuclear propulsion. Others focus on larger, more complex spacecraft that could carry more instruments and conduct more detailed studies. Each approach has its strengths and challenges, and ongoing research is helping to identify the most promising paths forward. Why strange planets matter. Before the discovery of exoplanets, our understanding of planetary systems was limited to the planets in our solar system. These planets seem to fit into a relatively neat framework: rocky planets close to the Sun, gas giants farther out, and icy bodies on the fringes. However, the discovery of planets like hot Jupiters, gas giants orbiting extremely close to their stars, shattered this tidy model. These worlds demonstrated that planetary systems could form and evolve in ways we never imagined. Take, for example, planets with highly eccentric orbits. These planets swing dramatically closer to and farther from their stars during their orbits, creating extreme seasonal changes that could profoundly affect their atmospheres and surfaces. Then there are planets with unusual compositions, like carbon-rich worlds or water-dominated planets. These strange compositions may arise from the specific conditions in their natal disks, the swirling clouds of gas and dust from which planets form. Studying these planets can reveal how varying amounts of elements like carbon, silicon, and oxygen influence planetary development. For instance, a carbon-rich planet might have landscapes made of diamond or graphite, while a water world could lack significant land masses entirely. These exotic conditions stretch our understanding of geology, climate, and potential biospheres. Planets like Proxima b, which endure constant flares from their parent star, might seem inhospitable at first glance. However, these extreme conditions could still allow for life, particularly if the planet has protective features like a strong magnetic field or a thick atmosphere. By studying such worlds, scientists can better understand how life might adapt to hostile environments, broadening the definition of what makes a planet habitable. One particularly intriguing category of strange planets includes rogue planets, worlds that drift through space without a parent star. These planets might seem like barren, frozen wastelands, but some could harbor subsurface oceans heated by internal radioactive decay or residual heat from their formation. If life exists on such planets, it would be completely independent of starlight, relying instead on alternative energy sources. Studying rogue planets could offer clues about how life might arise and persist in conditions vastly different from those on Earth. Consider gas giants orbiting extremely close to their stars, where temperatures can exceed 2000 degrees Celsius. The atmospheres of these planets are often inflated to immense sizes, with some even losing material to their stars due to intense radiation. Observing these processes in action helps scientists refine models of atmospheric dynamics, chemistry, and heat transfer. It also sheds light on how planets interact with their stars, a key factor in understanding the long-term stability of planetary systems. Observing these distant worlds often requires cutting-edge instruments and techniques. They demand extremely sensitive spectrographs capable of isolating minute signals. Studying planets with eccentric orbits or unusual compositions pushes the limits of computer modeling, requiring simulations that can handle complex interactions between gravity, radiation, and atmospheric chemistry. These advancements not only benefit exoplanet research, but also have applications in other fields of science and technology. And most of all, these strange worlds inspire curiosity and wonder. What would it be like to stand on a carbon-rich world surrounded by towering diamond mountains? Could a planet with eternal day and night have creatures adapted to each side? It taps into a shared curiosity for the unknown and a collective desire to understand our place in the cosmos. How do these strange and wondrous worlds make you feel? Leave your comments down below, and if you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.